Rational functions. We'll start by defining a rational function. A rational function is a function of the form p of x divided by q of x, where p of x and q of x are both polynomials. So this is a generic way to represent a polynomial, and what we need to remember about polynomials is that their exponents have to be whole numbers. So they cannot be negative numbers, the exponents cannot be 0, and the exponents cannot be fractions. So that would create a problem, and then we'd no longer have a polynomial. So similarly, we can't have any trig functions, any exponential or logarithmic functions have to be polynomials over polynomials, and because this is in a fractional form, we of course can never have the denominator equal to 0. So q of x cannot be 0 in the definition of a rational function. And so now we'll go ahead and look at some graphical examples of rational functions. Let's take a look at these two examples. I want to identify the domain of each of these functions, and then I want to find any x-intercepts, asymptotes, or holes in the graph. So there may or may not be x-intercepts, asymptotes, and holes. So these are two separate rational functions, and even though they're both rational functions, they don't look too much alike. They can look very different from each other. And before we attempt to find the domain, I actually want to go ahead and define what an asymptote is, because it's important to even finding the domain on a graph. An asymptote is a line that a function approaches near the end of the function. Near the end of the function. So the end of a function is like where positive and negative infinity live. So an asymptote, it's like a guiding line that tells us where the function is going towards the ends. So on this first graph here, I have a horizontal asymptote at this dotted pink line. So the pink line is actually not a part of the function. It's just a guiding line that's going to tell us at the ends of the function. So over here is positive infinity, over here is negative infinity on the x-axis. So near the ends of the function, my actual graph, the purple part, is getting closer and closer to this pink line. That's what makes this pink line, y equals 1, a horizontal asymptote. And then similarly, the function also approaches y equals 1 as I go towards negative infinity on the x-axis. So near the ends of the function, I'm approaching the horizontal asymptote. And then I can also take a look at the vertical asymptotes here at x equals 1 and x equals negative 1. And they too are lines that my function approaches, but now we're talking about as I go up and up and up towards positive infinity on, positive infinity on the y-axis and negative infinity on the y-axis. So I'm getting closer and closer and closer to negative 1 and positive 1, depending on what side I'm coming from on this particular function. And then down here, I'm getting closer and closer to negative 1 and closer to positive 1, depending on which side I'm looking at. So my function gets close to these two lines as I start to look at what happens towards positive and negative infinity. Now, a very important fact is that I cannot ever cross a vertical asymptote. So vertical asymptotes is where the denominator of a rational function equals 0. And that's not possible. I can never have the denominator of a fraction equal 0. So there's no way I can ever cross a vertical asymptote. Now it is possible to cross a horizontal asymptote, although this one does not. So now we can talk about domain. Domain is the collection of all x values that give us a y value. So on this particular graph, way over here at negative infinity, this graph is going to keep going on and on and on. It's going to get closer and closer and closer to this asymptote. So I'm going to hit every single x value way over here from negative infinity, or I should say every x value will correspond to a y value from negative infinity all the way up until negative 1. Now, negative 1, this graph is going to go up and up and up and up, but it's never ever going to cross this point at negative 1. So at negative 1, there's no output. There's not going to be any point on this vertical line. So I'm going to have to get rid of negative 1. And in interval notation, we're going to go ahead and say the domain is from negative infinity up till negative 1, and I do not want to include negative 1, so I use open parentheses. Now, right after negative 1, I start to have y values again. So right after -1 is where I want to pick up and continue on my domain to go from -1. Now again, I want to include another open parentheses because I'm not including -1. I want to pick up right after -1 and go all the way up until the next vertical asymptote, which is +1. So between -1 and 1, I hit all these y values here. So every x value corresponds to some y value between -1 and 1. Then I have to just go ahead and jump over 1 and then pick up again right after and go from 1 all the way to +infinity. So basically what this says is my domain is every single x value except for 1 and -1. So now let's go ahead and look at the second graph here, and let's talk about its domain. Now this graph only has a horizontal asymptote here at 2, and there are no vertical asymptotes, and there are also no holes in the graph. So any holes in the graph would also be x values I'd have to look at to remove from my domain. At wherever hole in the graph there was, I'd have to look at that corresponding x value and remove it. But there are no holes and there are no vertical asymptotes, so the domain here is -infinity to infinity. If I plug in any x value, I will get out a corresponding y value. So the domain here is all real numbers, which we express as -infinity to infinity, always open parentheses around infinities. So now let's move on to finding the x-intercepts of these two functions. So x-intercepts are any places where my graph crosses the x-axis, crosses or touches the x-axis. So in this case, I have a graph that is touching the x-axis at 0, 0. So my x-intercept, and x-intercepts have to be of the form a number, comma, 0. In this case, the coordinate point is 0, 0. So we want to make sure and write our intercepts in the proper form, which has to be a number, comma, 0, because the y-coordinate on the x-axis is always 0. And now moving on to finding the x-intercepts of the second function, if any. Well, actually there are two. So I have one x-intercept right here at -1, 0. And then we're just going to approximate because we're looking at a graph. Let's say this one goes through 0, 0, although it looks a little bit further to the left. So the x-intercept here, x-intercepts I should say, are -1, 0, and we'll go ahead and say 0, 0. One little subtlety I want to point out here is that I want you to recognize I separated these two points by a comma because they reference coordinate points. As opposed to over here, I separated these intervals by this little u, which means union or and. So it's very important to understand notation because then you're talking about two completely different things. How do we recognize that -1 to 1 is actually an x interval? These union signs tell us that this is different from the coordinate point, -1, 1. As opposed to over here, my x-intercepts are separated by commas. And now we'll go ahead and move on to the asymptotes. So we actually already said what each of the asymptotes were. Now I just want to focus on how we write them. So what I see a lot of times is students do this. They say the horizontal asymptote equals 1. That is incorrect. A horizontal asymptote has to be of the form y equals. They are horizontal lines. So the horizontal line is y equals 1. I don't just want to see HA equals 1. And the vertical asymptotes, in this case there are two, and they always have to be x equals because they are always vertical lines that are of the form x equals. So x equals 1 and x equals -1 in this case. And then on the second graph, we already said there were no vertical asymptotes, but there is a horizontal asymptote at y equals 2 if these little tick marks are each one unit. And then finally, there are no holes in either of these two graphs. All right, now we'll move on to two more examples with the same set of instructions. So two different graphs this time. Let's try to find the domain of each of them. So in this first graph, I have a vertical asymptote happening at the x value of +1. So that means I'm going to have to remove +1 from the domain because there will never be any corresponding y value when I plug in x equals 1 because I can't cross a vertical asymptote. And on this particular graph, I have something I didn't have in the previous two. I have a hole in it. And because I have a hole in it, that means there is no y value along this vertical line either, or at this particular x value, which happens to be -1. So I'm going to have to remove both -1 and +1 from the domain. So in interval notation, it's actually going to be the same domain we looked at in the first example. So -infinity to -1, I want to exclude -1, so open parentheses. And from -1 to 1, both open because I want to exclude -1 and 1, and everything from 1 to infinity. So every other x value corresponds to a particular y value, except for -1, because there's a hole in the graph and there's no other y value anywhere along that line, and at +1, because there's a vertical asymptote there and there's no way I can cross a vertical asymptote. And now taking a look at this last image, here I have a rational function, and hopefully you'll notice that there are no asymptotes drawn for us. But that's because this is trying to look like what your graphing calculator would look like. So on your graphing calculator, you won't see the asymptotes drawn. But what we can hopefully try to imagine is the vertical asymptotes being at x equals +1, so we can see that the graph is approaching +1 and approaching +1, and going down towards -infinity over here and going up towards +infinity over here. So x equals +1, that's going to be a vertical asymptote, and then towards x equals -infinity and x equals +infinity, my graph's getting closer and closer and closer to the x-axis, and the x-axis is the line y equals 0. And then same thing over here, as I get close to -infinity, my function, the purple part, is getting closer and closer to y equals 0. So those are my asymptotes. They're not drawn in, just like they wouldn't be drawn in on your calculator, but you'd still have to be able to recognize what they are. So once we recognize that, I now know I need to exclude +1 from the domain of my function. So the domain has to be -infinity to 1 and from 1 to infinity. So this says everything except 1 because of my open parentheses around 1. So now let's move on to finding x-intercepts of each of these graphs. So the x-intercepts on the first graph, sorry it's kind of light here, the x-axis is actually right here, and you can see that green dot is accentuating the x-intercept. So that green dot doesn't have to be there. A point doesn't have to be accentuated. Sometimes we just like to do it because it's an important point. So in this case, it is important. It's the x-intercept, and it's of the form x, 0, the x value being +3. So the x-intercept in this case is 3, 0. And over here on this graph, this function is approaching the line y equals 0 on both sides of the function as I go towards -infinity and +infinity, but it looks like we're approaching it and we're never going to cross it. So if I never cross it, again, it's possible to cross a horizontal asymptote, but based on this graph, I can see that I'm just going to get close to it. I'm never actually going to cross it. So that means I never cross the x-axis, so there are no x-intercepts for this graph. So rational functions don't have to have them. It's possible not to. Now asymptotes. So this is just going to be a matter of writing them out. We have talked about them already. The horizontal asymptote of this first function is going to happen at y equals 1. So that's this pink dotted line over here. And remember, horizontal has to be of the form y equals. And the vertical asymptote is at +1. And vertical asymptotes have to be of the form x equals. And then we did look at each of the asymptotes happening here. Our horizontal asymptote is the x-axis, or y equals 0. And our vertical asymptote was x equals 1. And then finally, we're asked to identify any holes, and one of our graphs has a hole in it. The hole occurs at this coordinate point, so holes have to be written as coordinate points, and they're not always a number, 0. I have a lot of students find or write that once they find the x value, they write it as a coordinate point and they let the y value be 0. So in this case, we can clearly see the y value is actually 2. So the hole occurs at the coordinate point -1, which we knew when we found the domain, that's the x value it happened at. But it's not -1, 0. The hole is specifically at the y value 2. So holes and x-intercepts have to be written as coordinate points. X-intercepts have to be a number, 0, because x-intercepts live on the x-axis. But holes do not always live on the x-axis, like this one here is specifically at -1, 2. Now we're going to move on. Instead of being given the graph of a rational function, we're going to be given a polynomial over a polynomial. So in general terms, I'm going to have ax to the m plus some terms and bx to the n plus some terms. So these are my leading terms of the respective polynomials. And if we're asked to find the domain, the x-intercepts, the asymptotes, and the holes, I'm going to advise that you follow these steps. So I'm going to advise that you first find any horizontal asymptotes. And to do that, we have to look at the leading terms, and specifically we have to look at the degree. So the degree of this top polynomial is m, and the degree of the bottom polynomial is n. So if m, the degree on the top, is less than the degree on the bottom, then the horizontal asymptote is y equals 0. It's important we recognize that it has to be the equation of a horizontal line, so y equals. So if the degree of the top is smaller than the degree of the bottom, the horizontal asymptote is y equals 0. If the degrees are the same, if m equals n, then the horizontal asymptote is y equals a over b. So a over b corresponds to the leading coefficient of the numerator over the leading coefficient of the denominator. Now, it doesn't always just mean the number in front of the first term and the number in front of in the numerator and the number in front of the first term in the denominator. It's the leading coefficient. So I went ahead and called this the leading term. So a is the leading coefficient, so the number in front of the leading term. The leading term is the one that has the degree, or if I want to break that down even further, the degree corresponds to the highest exponent of all of the x variables in all of the terms of the polynomial. So it's really important to know what all of those terms mean and be able to use them as fluently as I am. And then finally, if m is greater than n, so if the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. And in fact, what happens is there is a slant asymptote. But we're not going to concern ourselves with slant asymptotes in this class. So that's the rules for horizontal asymptotes. And once you've done that, then what I'm going to go ahead and advise you do, if it's not already in this form, is to factor both the numerator and denominator if possible. So if the polynomial in the numerator is a quadratic or in the denominator is a quadratic, which is often what we will have, then I'm going to advise that you factor to find those holes, x-intercepts, and vertical asymptotes. Now, they won't always be quadratics, but that's clearly going to be the easiest thing to factor. Now, to find holes in the graph, we want to find any x values that make both p of x, the numerator, and q of x, the denominator, equal 0. And holes must be of the form x comma y. So holes occur at coordinate points, as we saw when we looked at the graph. So we can't write a hole, the hole is x equals 2. That doesn't make sense. I have to write the hole occurs at an x value comma a y value. And what we have to do is, once we find that x value, we have to substitute that x value into the remaining function after linear terms cancel. So it's going to make more sense when we do an example, but this is just the general rules. To find x-intercepts of the graph, we need to set p of x being the numerator, equal to 0 and solve for x. But, and this is a big important but, those values cannot make q of x equal 0. So we're going to find all the x values that make the numerator 0, but if those values also make the denominator 0, they can't be x-intercepts. That's where holes in the graph occur. So we have to be really careful about that distinction. So it's not just always set the top equal to 0. We have to make sure that those values don't make the bottom 0, because then in fact we found a hole, not an x-intercept. And to find vertical asymptotes, we need to set the denominator equal to 0. We called that q of x, and solve for x. But again, those values cannot make now the top equal 0, because then we found a hole in the graph. So all of these you can see are sort of related to each other, and it's important to understand the distinction. And then, if we are asked to find the domain is all real numbers except those that make the denominator equal to 0, right? So in a rational function like a fraction, we don't want the bottom to be 0. So to find the domain of a rational function, we need to find all those values that make the bottom 0 and remove them from all real numbers, and write that in interval notation. All right, now let's practice. Let's find the asymptotes, holes, x-intercepts, and domain of the rational functions given, if any. So remember, there doesn't have to be asymptotes, holes, and x-intercepts. There's definitely going to be a domain, though. And then we're going to try to actually sketch the graph once we have this information. So the first function we're going to look at is x minus 1 over x plus 2. Pretty basic rational function. So if we follow the steps that I went ahead and suggested, we're going to focus on the horizontal asymptote specifically first. So we're going to look at the degree of the numerator. So if I look, I have x raised to the first power, so that's the highest exponent of x in the numerator. And in the denominator, I also only have x to the first power. So since the degree of the numerator matches the degree of the denominator, they are equal. My horizontal asymptote is going to be the leading coefficient of the numerator, so the number in front of this x to the 1, which happens to be a 1, over the number in front of this x to the first power in the denominator, which is also 1. So in other words, the horizontal asymptote is y equals 1. So remember, it has to be of the form y equals. We are not just going to write HA equals 1. So we have to write y equals 1. So now we're done with the horizontal asymptote. The next thing I said we would try to look for is holes in the graph. So the first step, though, prior to that would be to factor, but this is already actually in factored form for us. I have x minus 1, just one term, and x plus 2, or I'm sorry, one expression, x minus 1, over one expression, x plus 2. So there's no factoring that can be done here. So to find any holes in the graph, what we're looking for is any values that will make both the top and the bottom 0, any particular x values where that happens. And so you'll notice, hopefully, that the x value that makes the top equal to 0 is positive 1. The x value that makes the bottom equal 0 is negative 2. And those are not the same value, so there are not going to be any holes in the graph. And so then what we do is we're going to move on to find x-intercepts. So x-intercepts is any place where the numerator equals 0. So if I were to try to find x-intercepts, I want to set the top equal to 0. So x minus 1 equals 0. So x equals positive 1. And we have to just check that that doesn't make the bottom equal 0, but we already found there was no hole, so this isn't going to make the bottom equal 0. And now I have to write my x-intercept in proper form. It would be incorrect to leave my answer like this, as x equals 1, because x equals 1 is the equation of a vertical line. X-intercepts have to be of the form a number, comma 0, because they live on the x-axis. So that number is 1, and then the second value has to be 0. And then we move on to vertical asymptotes. Vertical asymptotes is where the bottom equals 0, provided that number doesn't make the top equal 0. So if I set the bottom equal to 0, I have x plus 2 equal to 0. So if I subtract the 2 to the other side, I get x equals negative 2, and I can and should leave my answer in this form, because vertical asymptotes are of the form x equals. So x equals negative 2 is my vertical asymptote. Alright, so now I found my asymptotes, holes, there were none, and x-intercepts. So now I want to find the domain of my graph. So the domain is all real numbers except for those that make the denominator equal 0. Those are going to cause problems. Well, we already did the foundational work for this. I already found that that one problem value is negative 2. So my domain is going to be all real numbers, negative infinity, all the way up to negative 2, but I don't want to include negative 2, so I put open parentheses, and everything from negative 2 to infinity. So this says everything except -2. Every other real number will give me an output in this particular rational function. And so now what I want to do is go ahead and graph. Here I have my xy plane, and I can already fill out all the information that I found, the asymptotes, the holes, and the x-intercepts. So I'm going to go ahead and sketch y equals 1 as a dotted line. Because remember, asymptotes are not actually part of the function, they just help us draw the function. So I'm going to draw a horizontal line at y equals 1. I'm going to go ahead and mark my x-intercept at 1, 0. So on the x-axis, I have my x-intercept at 1, 0. And my vertical asymptote is at x equals -2. So here's -1, here's -2. And I'm going to also draw that as a dotted line because it's going to help me to sketch the graph. All right. Now, what I'm going to do from here is I'm actually able to sketch one portion of the graph already. So asymptotes, remember, are lines that we have to approach near the ends of the function. So I know that I have to go through this one point. It's the only point I know on the graph so far. So if I have to approach this asymptote, here's what's going to happen. I'm going to have to go through this point, and I'm going to have to approach this line. And I'm also going to have to approach this vertical line down here. So I am actually going to have to go down and approach this vertical asymptote. So this portion of the graph is going to look like this little curve here. And remember, I cannot cross a vertical asymptote. And if I wanted to even be a little bit more technical with this, I could find this y-intercept. To find y-intercepts, we let x equals 0. So if I let x equal 0 in this function, so in other words, this is y equals x minus 1, so 0 minus 1 over 0 plus 2, what I have is -1/2. So my y-intercept is 0, -1/2. So I obviously missed a little bit. This doesn't look like -1/2, but that is the true value on the graph that I cross on the y-axis. So -1/2 is my y-intercept, and this is what this portion of the graph is going to look like. Now, I have two options over here. I could either have a graph that's up here, or I could have a graph that's down here. Now, if you notice, this option here, both approach this horizontal asymptote and this vertical asymptote. So does this one. It approaches this horizontal one and this vertical one. So how do I know which one to choose? Well, this bottom one would have to cross the x-axis, which would mean there has to be another x-intercept. And we know that there's not. We only know that of the x-intercept at x equals 1. There are no others. So that means that it cannot be this bottom portion. It has to be up here in this top left-hand corner that approaches this horizontal asymptote at 1 and this vertical asymptote at -2. So this portion should not be here. So this is the sketch of my graph, and you'll notice it corresponds to the domain. I am having a corresponding y value for everything except -2. And my vertical asymptote is the only problem. Moving on to a second example, I have f of x equals x squared minus x minus 6 over x squared minus 4. So the first thing we're going to do is find the horizontal asymptote, comparing the degree of the numerator and the degree of the denominator. So here I have a quadratic and a quadratic. They are the same degree, so I'm going to have the leading coefficient over the leading coefficient, which happens to be 1 again. So I have y equals 1 as my horizontal asymptote one more time. And so now I'm going to have to attempt to find any holes in the graph and x-intercepts and vertical asymptotes. So before we do that, we're actually going to factor these quadratics, and so I'm going to do that a little bit quickly here because we're not reviewing that topic now. So the top's going to factor to x minus 3x plus 2, and the denominator is going to factor to x minus 2x plus 2, as it is the difference of squares. Alright, and in this form, I'm able to see quite a bit more that will help me find those remaining portions. So the next thing I wanted to try to find is any holes in the graph. Now, holes are going to be values that make both the numerator and denominator 0. And here's the nice part about having a factored numerator and denominator. if I see the same linear terms, which I do here, I see an x plus 2 and an x plus 2, I know there's going to be a hole in the graph at whatever x value makes that term equal to 0. Because if the same term is repeated in the numerator and denominator, whatever makes that term equal 0 on the bottom will make that term equal 0 on the top. So that value is negative 2. If I plug in a negative 2 on the bottom, then 0 times anything is 0. If I plug in a negative 2 on the top, same thing, I end up with another 0 on the top. So any value that makes both the top and bottom equal 0, that's where the hole is going to occur. So my hole is going to occur at negative 2 comma something. And to find that something, here's what I need to recognize, is that when I cancel these linear terms here, I have a remaining function left over. That remaining function is x minus 3 over x minus 2. So we have to be careful with this equal sign right now. What this is saying is that x squared minus x minus 6 over x squared minus 4 is equal to x minus 3 over x minus 2, except at the point, or the x value, negative 2. So this original function is equal to this function when I've canceled out the x plus 2 terms from the top and bottom, except at negative 2. At negative 2, there's a hole in the graph where I have to take negative 2 and substitute it into whatever is left over. So I'm going to do that scratch work here on the side. I'm going to plug negative 2 minus 3 over negative 2 minus 2. So the top is negative 5 over negative 4, which is 5 over 4. So the hole occurs at negative 2 comma 5 over 4. So I have to write it as a coordinate point. I cannot just write at x equals negative 2 because that's the equation of a vertical line. So now that we found the hole in the graph, let's move on to try to find the x-intercepts. So now to find the x-intercept, I'm going to use the remaining portion of the graph. There's no need to go back and look at this graph where I already crossed out the x plus 2's. It's like I already handled the x plus 2 when I found the hole in the graph. So now it's like we're going to be dealing with this nicer, smaller function. So to find x-intercepts, I set the top of this equal to 0. So x minus 3 equals 0. So x equals 3. And remember, we have to write this as a coordinate point. So 3, 0 is my x-intercept. And notice that value doesn't make the bottom equal 0. We already found the only number that does that is negative 2. And finally, to find vertical asymptotes, we're going to set the bottom, again, of my nicer, smaller function equal to 0. So if I set x minus 2 equal to 0, I get x equals positive 2 as my vertical asymptote. So here are all the components to my graph. The last thing I'm going to do is find the domain. So now, the domain is any x values, or all x values, except for those that make the bottom equal to 0. And we're talking about the domain of the original function here. Well, the original function was x squared minus 4, or x minus 2x plus 2. So the domain is everything except positive 2, because that will make this part equal 0, and negative 2. I have to throw out both of those values. So the domain is negative infinity to negative 2, open, negative 2 to 2, open on both, I don't want to include those numbers, and from 2 to infinity. So here's my domain, which basically says everything except negative 2 and positive 2. Now let's graph this thing. So let's graph the horizontal asymptote, which is at 1. So again, we're drawing it as a dotted line. It's not actually part of the function. I will draw the vertical asymptote at positive 2. So we'll say over here is positive 2. We know there's an x-intercept at 3, 0. So x-intercept meaning on the x-axis. So there it is at 3, 0. And we know there is a hole in the graph at negative 2 and then 5 over 4. So 5 over 4 is a little bit bigger than 1. So here we'll go to negative 2. And then since it's a little bigger than 1, and the horizontal asymptote's at 1, it's going to have to be a little bit higher than that. So there's a hole there. I'm going to redraw it because it doesn't quite look like a hole, it looked like a dot. So I'm going to go ahead and put there is a hole right there in the graph. So now I have to sketch this graph. And one of the options for any function to plot points is just to plug in x to get out y values. But that's not really even necessary on this graph, just like we didn't plot any on the last graph, because we have these important points, or in this case, a hole and a point. So I know that I'm going to have to approach my asymptotes, and I'm going to have to go through this x-intercept. It is a point on the graph. So I'm just going to go ahead and sketch the portion of the rational function. It's down here in this bottom right hand corner. And because there's a hole in the graph, I know that the function is going to have to approach, whoops, that doesn't look too right. It's got to approach this asymptote, and then it's going to have to approach this vertical asymptote up here as well. So there's a hole in the graph, so that means the graph itself has to be up here in this top left little quadrant that we've made between the asymptotes. And then again, just like last time, I know that I can't be down here in this portion because then I would have to cross the x-axis, and we know there are no other x-intercepts. So the hole in the graph really told us a lot about the shape of the graph and where its location would be. We could also confirm this is in the right area by finding the y-intercept, which is actually pretty easy. We set the x values in the original function equal to 0, or even in the reduced function if we want. We could set the x values equal to 0, which means that we'd end up with 0 minus 3 over 0 minus 2. So that's positive 3 halves. So my y-intercept is 0 3 halves, and 3 halves is above 1. So this value right here would be 3 over 2, or 1.5. And we would have got that if we plugged in x equals 0 over here, because we would have got negative 6 over negative 4, which is 3 over 2, or 1.5. And on to the last example, and this one's going to look a little bit different. So I have x squared minus x minus 2 over 2x minus 4. So if we start with trying to find the horizontal asymptote, we have the degree of the numerator is 2, and the degree of the denominator is 1. So when the degree of the top is bigger than the degree of the bottom, then there is no horizontal asymptote. So I'm going to go ahead and write none. Then the next step would be to find potential holes, x-intercepts, and vertical asymptotes. But before we do that, we factor. So I'm going to factor the numerator. I'm going to get x minus 2, x plus 1. And if I factor the denominator, all I can do is factor out a 2 between these two terms. So I'm going to have 2 times x minus 2. And hopefully what pops out at you is that these two linear terms cancel. So because these two linear terms right here cancel, there's going to be a hole in the graph at that x value. At the x value that makes these terms equal to 0, which is positive 2. So I'm going to have a hole at 2 comma something. Now again, to find that something, we're going to cancel those two terms out and see what's left over. What's left over is x plus 1 over 2, except not at 2. I have to include that condition. This means except not at 2. Otherwise, I cannot write these equal signs. We have to be really careful about when we write equal signs this year. So this rational function is equal to this function here, x plus 1 over 2, except at the x value 2 where there's a hole. The hole is going to be at 2 comma, let's see what happens. If I plug in a 2 into this x, I'm going to get 2 plus 1 over 2. So at 2 comma 3 over 2 is the location of my hole. And now I have this function left over. And before I try to find any x-intercepts or any vertical asymptotes, what I want us to recognize is that this is no longer a rational function so much as it is a linear function, because I really have x to the first power and no other x's, and this x to the first power is in the numerator. So this 2 on the bottom can be divided by both terms on the top. So I can rewrite this as 1/2 x plus 1/2, which is the equation of a line. So I took x over 2 plus 1 over 2, and then I rewrote x over 2 as 1/2 x. So this is now a linear function. So in a linear function, there are no vertical asymptotes. But there is going to be this hole in the graph that we found because it was a linear function, but it was really this original rational function that has a hole. And it does have a x-intercept, which can be found by, if we want to, set the top equal to 0. So our x-intercept, by setting the numerator equal to 0, I'm going to have x plus 1 equals 0, so x equals negative 1. And I again have to write that as a coordinate point, but there aren't going to be any vertical asymptotes. Those don't exist on lines. So now we're going to graph this thing. Well, to graph lines, we can plot their y-intercept. So I'm going to go ahead and say that this is 1/2, and my slope is 1/2. So I'm going to go up 1 to the right 2. So if I go up 1, that's going to take me to 3/2. And then I'm going to go right 2. So 1, 2. And this is definitely not to scale, obviously. This is just a sketch. So I'm going to go up 1. That would bring me to 3/2. And then over 2 would bring me to 2. And then I know that my x-intercept is negative 1. So I'll try to make it so that it's going to look like a line when I draw it right now. So I'm going to go through these points. And this is the line 1/2 x plus 1/2. But remember, our original function wasn't exactly a line. It was a rational function. It turned into a line with a hole in it. So the hole is at 2 3/2, which that was our actual second coordinate point over here. So I'm going to have to white that out a little bit, or I'll just go ahead and turn it into an open circle here. So we'll say that that is my hole in the graph. So there shouldn't be that little line through it. So it's going to be this line with a hole in it. So that was the graph of this rational function. So that's what we started with, but it ended up looking like a line. So rational functions can look like all kinds of crazy things. They can have asymptotes, they cannot have asymptotes, they can have holes, they cannot have holes. It really just depends. So you want to find out as much as you possibly can through the means of horizontal asymptotes, holes, x-intercepts, vertical asymptotes. We actually skipped domain. We should go back and find the domain real quick. The domain of this function is everything that doesn't make the bottom 0. Well, the only thing that made the bottom 0 was 2. And that makes sense because at 2 there's a hole, so there's no corresponding y value. So the domain is everything except for 2. So we include open parentheses around 2.